Hey everybody, in this video we are going to take a Unit 10 test based on the topic of equilibrium. All of these questions will be multiple choice and all of them come from the Chemistry Olympiad, so some of them might be hard, but regardless, let's try our very best to solve these questions. So without further ado, let's begin. Number 1. Silver sulfate with this molar mass has a Ksp equal to 6.0 times 10 to the negative 5. What mass of silver sulfate will dissolve per liter of water? So, we're trying to find the solubility in terms of grams per liter of water. So, this seems to me like a question where we have to find the solubility from the Ksp, and from the solubility we have to kind of convert it to this. So in order to do that, I think I have an idea. Let's first write the reaction for the dissolution of silver sulfate. So we know that silver sulfate looks like this, Ag2SO4, and that's a solid, and it will be in equilibrium with the dissolved components, 2 silver pluses, and 1 sulfate ion. Now, I think this question needs an ice chart because we're trying to find the molar solubility so that we can find the solubility in grams per liter. And if you remember, we can find the molar solubility by doing a little bit of math using the Ksp. So let's try doing that. So we have to first draw an ice chart, of course. So let me go down here and make an ice chart. So we have I, C, and E, and we will separate those into columns and rows. So we know that we start off with a lot of this and none of this. And then we're going to subtract 1 molar of the silver sulfate once it dissolves. And for every molar of silver sulfate that dissolves, 2 molar of silver ions are formed and 1 molar of sulfate ions are formed. So these are both pluses and that's a minus, but in the end you still have a lot and you have 2x here and x here. So we have this now. Now we have to write the equilibrium expression. So the equilibrium expression is quite easy to write actually because we're writing it for just the products because these are only the aqueous components. So we can write it like this, Ag plus squared because of the coefficient 2, and sulfate, and that's all. And let's plug in the variables that we got at equilibrium, which is the point where the maximum amount of the silver sulfate will dissolve. So that's at equilibrium, and we have to take these numbers and chug it into our equilibrium expression. So I think it's going to be 2x squared times x. And now let me do some erasing. So I'm going to erase all this. And I know that this is going to be the Ksp, and the Ksp is equal to 6.0 times 10 to the negative 5. Now we can actually simplify this because it is simplifiable, and that was the wrong button, sorry. So I have to use the eraser to erase this. And we know that 2x squared will become 4x squared once you distribute the 2, and you're simply multiplying that by x, and you should notice that this x will multiply out with the x squared to give us an x cubed. So we simply have to solve this. So we go 6 times 10 to the negative 5 divided by 4, and I get on the right hand side, so let me do some erasing on this side. So once I do the erasing, we see that x cubed will equal, let's see, 1.5 times 10 to the negative 5. And we simply take the cube root of both sides to get x on its own. And doing the math, if I take the cube root of this answer, I get that x is going to be equal to 0.025. And let me actually keep one sig fig just in case. So I'm going to keep one extra sig fig beyond the amount that I'm actually supposed to have. So 0.0247, and I'll underline it there to show 2 sig figs. And remember, X is also the molar solubility, since if you remember, minus X is the amount of the salt that dissolved. So this means that X must be the molar solubility. So we have the molar solubility. So let me actually erase all of this because it's kind of getting in the way. So I'm going to erase everything except for the X. So we know that the molar solubility is around 0.0247 moles per liter of solution. And they want to know the amount of grams that dissolve per liter of water. Now, in this case, since silver sulfate has a relatively low Ksp, this means that the molality, if you remember, which is, moles per kilogram of solvent, will be similar, and moles per kilogram of solvent is related to grams of the stuff over liters of the solvent, which is water. So in this case, we are going to assume that the liters of solution is going to be equal to the liters of water, since essentially by adding a little salt, the volume won't change that much. So a liter of solution will essentially be equal to a liter of water. So let's actually convert this number into grams per liter, and that's done by molar mass. So we know that for every mole, there's, of course, 311.87 grams. And remember, this is moles of silver sulfate, and this is the molar mass of silver sulfate. And multiplying these out, you cancel out the moles, and you're left with, let's find out, so times 311.87, and I get around 7.7 grams per liter of solution, and this is essentially equal to 1 liter of water, so it seems like our answer for number 1 will be D. Alright, let's now move on to number 2. So, for number 2, I'm going to open a new doc, and this is the question. IBR is in equilibrium with I2 gas and Br2 gas at 150 degrees Celsius. Here's the reaction, and here's the K for the reaction. Initially, a closed vessel at 150 degrees Celsius has a partial pressure of IBR of 0.350 atmospheres, so let's write IBR is equal to 0.350 atmospheres, and partial pressures of I2 and Br2, each of 0.750 atmospheres. So the pressure of I2 is equal to the pressure of Br2, which is equal to 0.750 atmospheres. What is the partial pressure of IBR once the system reaches equilibrium? So we have 4 answer choices, and let's just do the math and figure it out. So we know that the K for this reaction can be written as products over reactants. And I kind of just covered up the reaction. So let me do some erasing, and that just erased everything. So let me backtrack, and let's just, deal with what I did. And let me try undoing it. Oh, there you go. Okay, so the K is equal to, let's use a nice color this time. Let's use a green. So the pressure of I2 times the pressure of Br2 over the pressure of IBR gas, and you square that because there's a 2. Now we have the pressures that are not at equilibrium, and we have to have it at equilibrium, so we probably have to do an ice chart for this. So down here, I'm going to do an ice chart. So I know my reaction, so let me do this in a different color once again. So I know that it's going to be reactants going to products. So 2IBR gas is in equilibrium with I2 gas, and Br2 gas. And let's see if I have enough space for this table. It's going to be a little bit crushed, but it's perfectly fine, honestly. So, we start off with 0.350 atmospheres of IBR. So, let me do this in black, actually. 0.350. And we start off with 0.750 for each of these two. And we need to figure out which direction this reaction will go. So to do that, we can find the Q, or the reactant quotient. So Q is equal to, the same exact expression, but we just chug in the numbers. So 0.750 times 0.750 all over IBR squared, 0.350 squared. Doing the math, 0.75 times 0.75 divided by 0.35 squared yields a Q value of, well, let me erase this first because I whoa, what happened there? I don't think that was supposed to happen. Give me a second. I have to use the correct tool. There you go. So the Q is equal to around 4.59. Now we know that our K is 8.5 times 10 to the negative 3. And that's really hard to see, but that's a 10 to the negative 3 there. So since Q is greater than K, this means that we have too many products. So the reaction will go backwards. So now that we know that the reaction will go backwards, we can actually do something really cool. So we can erase this and say that this reaction will go backwards until it reaches equilibrium. So this stuff will be lost, minus x, and this will be plus 2x. Now, in the end, you'll get 0.750 minus x on each side, and you'll get 0.350 plus 2x on that side. So we got this cool thing, and now let's just chug in these expressions at equilibrium into the equilibrium expression in order to figure out what x is. So I'm going to do some erasing. So let me change the brush size so I could erase everything. So let's do some erasing now. And now that we're done, let's say that the K, which is 8.50 times 10 to the negative 3, is equal to, well, it's going to be products over reactants. So our products are going to be 0.750 minus x times the same thing, so it's squared, all over the reactants. So our reactants has 0.350 plus 2x. But remember that our reactant has the coefficient 2, so we have to square all that. And we have this nice equation, which you can actually do this to, and that actually cancels out the squares, so you don't have to use the quadratic equation. So let me do some math. 8.5 times 10 to the negative 3, and you take the square root of that, I get that 0.0922 is equal to 0.750 minus x over 0.350 plus 2x. And let me do some erasing to give me some extra space. So I'm going to erase that, and now let's actually distribute this here by multiplying both sides by this. So 0.0922 times 0.350 is going to be 0.0323, and you're going to add that to 2 times 0.0922, and you're going to chug an x at the end. 0.184x is equal to 0.750 minus x, and I don't like that minus x, so I'm going to actually move that to the left-hand side by adding an x to both sides. So adding an x to both sides will change 0.184x to, well, 1.184x. And now we have to subtract this from both sides. So 0.75 minus 0.0323 gives us this. 1.184x is equal to 0.718. Now to solve for x, we just do some math. So that number divided by 1.184, we get that x is equal to 0.606. Now they only want the partial pressure of IBR once the system reaches equilibrium. We found the x value that satisfies the point where these three will be at equilibrium. So we have to find the concentration of IBR at equilibrium, and we have an expression for that. The concentration of IBR at equilibrium is this guy over here. So we have to chug x here to figure out the equilibrium partial pressure of IBR. So we can use a different color this time. 0.350 plus 2 times x, which is 0.606. So doing the math, we multiply that by 2 and we add 0.35. And I get that the partial pressure of IBR is going to be 1.562 atmospheres. And it looks like C is our answer. Alright, let's now do number 3. The tetraamine copper 2 ion, CuNH3 2+, has a formation constant Kf of 1.1 times 10 to the 13. What is the minimum concentration of free ammonia in solution required to ensure that at least 99.9%, let's write that as a decimal, 0.999, out of the whole of the dissolved copper 2 ion is found in the form of its ammonia complex? So before we continue, let's think about what free ammonia means. So this actually means the ammonia that's left over at the end, or in other words, the minimum concentration of ammonia at the end of the reaction once everything has reached equilibrium. So it's like the free ammonia that's floating around after everything is all said and done. So let's first write the reaction for the formation of this ion. So we know that we start off with copper 2+, and we're going to have 4 ammonias because there are 4 of them. And when you combine them, they are in equilibrium. And we know that we are going to form the complex ion, which has a very cool name, which I'm not going to say. And this is aqueous. So what we have to do now is create an ice chart because we want to find the point where at equilibrium 99.9% of this stuff is turned into this stuff. So let's make a cool little ice chart because ice charts are cool. So we are going to draw our table here, and we know that we have no products. So the reaction will most definitely go forwards because it needs to produce some products to reach equilibrium. And if we were to do the Q would equal 0 because there are no products. And since Q is less than K, that means that the reaction goes forwards. So we already know that it will go forwards. And now let's write the concentrations. So they actually don't give us any concentrations. That isn't good. So what we do is that we use a variable. So the variable I am going to use to represent the concentration of copper 2 initially is going to be the letter N. Now it wants 99.9% of this to be gone and turn into this. So 99.9% or 0.999% of the N will have to react to form this. And we know that at the end, we will have 0.001 N left over. Now for every 0.999 N that is consumed, there is 4 times as much NH3 that is consumed. So we multiply negative 0.999 N by 4 to get negative 3.996 N. And we know that we will produce the same amount that we lost because it is a 1-to-1 ratio. So for every 0.999 N lost here, it will gain 0.999 N in terms of molar. Now we know that the concentration initially for NH3 is some unknown value that we don't know of. So I'll denote it as the concentration of NH3 initially. And we know that we start off with no complex. Now let's just go down and find our equilibrium expressions for each of the concentrations. So we get the concentration of NH3 minus 3.996 N, and let me make the size smaller so that it's easier to write with. So this will be 0.999 N, and note that everything that's within here is known as the free ammonia concentration. So this is what we're trying to calculate essentially. So don't forget that when we're doing this question. Now we have to actually go back up. So let me try scrolling back up. And we need to now write an equilibrium expression for this reaction. So what I will do is that I will erase the ice table. So I have to erase this so that I have some space to work with. And I will, of course, leave the equilibrium expressions at the end so that I could use them later on. And yeah, so let me switch back to the brush. And this is 999N, and that's a point. And we know that these are our equilibrium concentrations. Now, the Kf is simply equal to products over reactants, and since all these are aqueous, we are going to include all of them. So the concentration of copper and 4 NH3s attached will be divided by the concentration of copper 2+ times the concentration of ammonia to the 4th power. Now we know what these values are because we just simply calculated it down here. So what we will do is that we will replace our Kf with the actual number and the equilibrium expression with actual numbers. So our Kf is, let's see, 1.1 times 10 to the 13, and this is set equal to, well, let's see. So if I scroll down, I know that we put this first, so 0.999 N over the concentration of copper, which turns out to be 0.001 N, and we have to multiply that by the concentration of ammonia to the 4th power. Now, what I want to do is to simplify the process. All of this is essentially the free ammonia concentration. So I'll just say that the variable will be the concentration of NH3 free, which represents all this stuff, by the way. And this only allows me to simplify the process to make it easier to see. So this is the free ammonia concentration, or all this stuff, but we wanted to write it like that because it's easier to see that way. And notice how immediately we see that the N's cancel out. So that's a good thing, because that means that our only variable is the free ammonia concentration. So 0.999 divided by 0.001 turns out to be 999. So I'm going to cross this out and write 999 with 1 sig fig here. Now, we essentially have this is equal to 999 over this to the 4th power. So let me do some more erasing. So let me erase all this stuff since we don't need it anymore. And let's see. So we can do 1.1 times 10 to the 13 is equal to 999 with 1 sig fig over the free ammonia concentration to the 4th power. And we can flip these two to say that 999 over 1.1 times 10 to the 13 is equal to the free ammonia concentration to the 4th power. Now, if we want to cancel out the 4th power, we simply have to take everything to the 1/4 power. So, if we take everything to the 1/4 power, essentially, the 4th power disappears here, so I'm going to erase that. and I have to simply chug that into my calculator to calculate the free ammonia concentration. So 999 divided by 1.1 times 10 to the 13, and we take that to the 1/4 power, and I get that the free ammonia concentration, which I will do in green, so the free ammonia concentration is going to be equal to, let's see, 0.003. So which answer choice works? Well, 0.003 is D. So D is our answer for number 3. So now let's do number 4. Number 4, what is the equilibrium expression Kc for the reaction shown here? So let me use the color black and let me make my brush size a little wider. So they want the Kc for this reaction. We know that Kc is simply products over reactants, and in this case, it seems that even though they are gases, it seems like they want us to find the concentrations of the gases instead of their partial pressures. So that's kind of odd, but that's fine because we know how to do that, because we know that Kc is for concentration. And yeah, so let's get going. So products, we have SO3, and we square that, and we put that over our reactants, and we notice that the solid is not added to the equilibrium expression because solids have an activity of 1. So we don't include sulfur. What about the O2? Well, yeah, let's add the O2. So we have 3 of them, so the concentration of O2 to the 3rd power, and this is equal to Kc for the reaction. And it seems like the answer choice that best fits this is D. Number 5. In which reaction at equilibrium will the amount of reactants present increase with an increase in the container volume? So if you remember, an increase in container volume means that the pressure is going down. So volume goes up, pressure goes down. This is in accordance with PV equals nRT, where P and V are inversely related for a constant N, R, and T. So, increasing volume decreases pressure. Now, we know that decreasing pressure means that it will favor the side with more moles of gas. Because if you think about it, at higher pressures, we want to produce the side with less gases. So if there's a lower pressure, the opposite will happen, and we will have to find the side with more gases, and that's where the reaction will go from equilibrium. So originally we're at equilibrium, but we decrease the pressure, and we want to shift toward the side with more gas moles. So which side has more gas moles for A? Well, it seems like they're the same. Actually, no, they're not the same. So this is a solid, which doesn't count because it's not a mole of gas. We have 1 mole of gas here turning into 2 moles of gas. So, since there are more moles of gas here, that means that by lowering the pressure at equilibrium, we are going to be shifting to the side with more gases. So this will shift to the right, and that will not increase the reactants. That will increase the products. So A is not an answer. Now what about B? Well, for B, we have 1 mole of gas and 1 mole of gas producing 2 moles of gas. So the change in the moles of gas is 0. So increasing or decreasing pressure will not shift the equilibrium for this one. So B is out. Now what about C? Well, it seems like C is the same deal. We have 1, 1, 1, 1, or a total of 2 moles of gas on each side. The change in the moles of gas is 0. So C is out as well. Now the only thing that it could be left is D. So D is our answer. Let's figure out why. So we have 4 moles of gas and we have 2 moles of gas here. The side with more moles of gas will be favored at lower pressure. So because of that, this reaction will shift to the left because there are more moles of gas here. So that means that D is our answer for number 5. Let's move on to number 6. So a 500 ml saturated solution of magnesium carbonate is reduced to 120 mL by evaporation. What mass of solid, MgCO3, is formed? And they give us the Ksp, which will be pretty important. So we have to first understand what's going on before we can do some math. So we start off with a container with 500 mL of the saturated solution. So that means that the maximum amount of salt was dissolved in there. So let's say that X is the maximum amount of salt that dissolved in the 500 mL of solution. Now, they say that they do some evaporation. Maybe they put it under the sun, so I could draw a sun over here with the right color, of course. So they put it out in the sun, and they kind of just evaporate it. So once they evaporate it, we have, less water, and we have 120 mL of solution now. And we know that 120 mL of water can dissolve less than 500 mL of water. Why do we know that? Well, if you have more water, you can dissolve more stuff. If you have less water, you can dissolve less stuff. So it's using a bit of common sense here and there to understand what's going on. Now we know that the amount of salt that dissolves here will be less than how much dissolves in here. So it might be, let's take a guess, maybe only 0.2 of the original amount of salt dissolved, and that would be equal to the amount of salt that was soluble. So by decreasing the volume of our solution, we were able to dissolve less stuff. So why am I talking about this? Well, let me use a different color now. So originally you had 500 mL of a saturated solution. This means that you have the maximum amount of salt dissolved in there. So let's just say that X was the maximum amount of salt that could dissolve in that amount of water. But once you do some evaporation, don't you think that that amount of water can dissolve less salt? But didn't you start off with this much salt, but now you can only dissolve this much? Where does the excess salt go? Well, the excess salt actually precipitates out as a solid because it can't dissolve in there. Because at first you had a lot of salt. But in the end, the water said, I can't dissolve that much, so you're going to have to not dissolve anymore. So there will be still, a saturated solution of MgCO3 here, but of course there will be less amount of salt dissolved, and the excess salt will precipitate out because there's just too much of it for that little amount of water. So now that we understand the problem at hand, let's figure out the math at hand, since you kind of have to do that to solve this question. So I'm going to erase all of this, and let's now figure out what's going on. So we need to find out the molar solubility of magnesium carbonate first in order to find out how much dissolved initially in the 500 ml tank. So we can easily do this by writing the reaction. MgCO3 solid becomes Mg2 plus aqueous plus CO3 minus aqueous. And I think that over there says 0.27 grams. Sorry if you can't see that, but it's there. So let's see, what else do we have to do? So I think what we have to do is create an ice table. So ICE, we start off with lots of this, minus x plus x plus x. We start off with nothing initially because at the beginning you have a pure solution with nothing and you add the salt in there and you can see, how much can dissolve, and that will be x. So you have a lot left over, you have x and x. So now the next step is, of course, to write the equilibrium expression, or the Ksp, for this reaction. So let me do some erasing and leave the equilibrium stuff left over so that we could deal with that. So I'm going to write the Ksp expression, and that's equal to Mg2 plus times CO32 minus. And you notice immediately that you could just plug these two in here, and you realize that Ksp is equal to x squared. Now, Ksp is equal to 4.0 times 10 to the negative 5, and if we want x, we simply square root both sides, and if you square root both sides, these two cancel out, and we're left with x. So, using my handy-dandy calculator, 4 times 10 to the negative 5 is, a number, and I take the square root of that, and I get that the molar solubility, or x in this case, is 0.0063 molar. So let me put a capital M there. Now that's not the question. If that was the question, it would have been done. But no, we have to do just a bit more. So I'm going to erase all of this, and we're going to do the second part of this question, which is to determine how much precipitated out. So let's see, over here, 500 mLs is also 0.500 liters. Now we need to figure out how much salt is in 500 mLs, or 0.5 liters of solution. Well, we know the molarity of a saturated solution, and we know the volume of the saturated solution, so just multiply this by 0.0063 moles per liter of solution. Remember, molar is moles per liter of solution. So that's what I did there. So 0.5 times that number is going to be 0.003. Let's see. I'm going to keep an extra sig fig. So 0.00316 moles of the salt. Now this is the amount that dissolved in here. Now we need to figure out how much salt dissolves in the new evaporated solution in 120 mLs, or 0.120 liters. Let me check if that's the right number. Yeah, I got it right. So we multiply this by the molality, so 0.0063 is equal to, let me check, 0.12 times 0.0063. We get 0.00076 moles of the salt. So before, we could dissolve this much stuff, but after, we can only dissolve this much. So this means that some of the stuff had to be undissolved because the solution's like, hey, I can't dissolve all that. I can only dissolve this much. So the leftovers will be precipitated. So to find the leftovers, we take the amount that we had initially, 0.00316, minus the amount that we could dissolve. So let's see, we could dissolve 0.00076. Doing the math, 0.00316 minus 0.000756 will leave us with, well, let me get an eraser because it's getting increasingly messy because I write pretty big. So we are left with 0.0024. Let's see if I followed the sig figs correctly. So I have it here, so I can only keep 4 decimal places at most. So we have left over 0.0024 moles of the magnesium carbonate, and this is the amount that precipitated. Now, if you want to know why I subtracted these two numbers, think about this. The amount that precipitated plus the amount that stayed dissolved is equal to the amount that dissolved at the beginning. Because at the beginning, we had the 500 mLs and it was saturated, but afterwards, only a part of it was dissolved and the rest of it precipitated. So this is kind of like the conservation of mass. So we have this, but that's not the answer choices. We have to turn this into grams. So in order to turn this into grams, we multiply 0.0024 by the molar mass of magnesium carbonate, which is 84, and we get 0.20 grams that got precipitated. Now, I know that I erased it, but you can see very faintly that it says 0.20 here, and if you replay the video, that's what it says, and therefore our answer will be C. Number 7. The diagrams below represent the progress of a reaction of A to B, with molecules of A represented by solid circles and molecules of B represented by open circles. Which statement best describes the reaction at T equals 1000 seconds? So first, let's take a look at the images to see what's going on. It seems like at first it's all A, and then as you go on, you see that there's more and more B, probably because the A is becoming B. So in the second image, you can see 6 white dots, or 6B, being formed, and in the third image, you can see, well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 open circles. And at T equals 1000, you can also count the number of white circles, and let's see, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 open circles, and just in case, let's count the number of black circles as well. So there's 4 there, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 shaded circles, and how many shaded circles are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it seems like the amount of particles stay the same, because if A turns into B, there's still one particle. So in the end, the number of particles will add up to 20 in this closed container. So there are 1, 2, 3, 4, 5, 6, 7, 8 shaded circles, and 2, 4, 6, and 8 shaded circles. So now that we know the progression of this reaction, and we know the ratio between the products and reactants for each of these, let's figure out what happens at T equals 1000 seconds. A. The reaction is at equilibrium because the concentrations of A and B are no longer changing. Now this does seem right, because from T equals 100 seconds to T equals 1000 seconds, you can see that the concentrations are fairly the same, and because of that, that means that the reaction has stopped and essentially the forward and backward reactions are equal. And that's what equilibrium means. It's when nothing is happening because the forward and backward rates are the same. So I have a feeling that A is the answer, but let's read the other choices. The reaction is not at equilibrium because not all of the A has been consumed. Well, for things to be at equilibrium, it doesn't mean that all of this has to turn to this. Remember, equilibrium is like a balance between products over reactants. So there can still be products in the end during equilibrium, even though not all of the reactants reacted, because in equilibrium, both reactants and products exist in equilibrium. So B is out. C. The reaction is not at equilibrium because the concentrations of A and B are not equal. Well, that's not what equilibrium means, so C is out. Because there could be more products than reactants, or maybe there could be more reactants than products. We never know what the equilibrium is between the two unless we are given a constant. What about D? The reaction is not at equilibrium because the position of the molecules are still changing. This is wrong because equilibrium has nothing to do with the position of molecules. Just because something moves around doesn't mean that it disappears. It's still there. Like, even though this black circle went over here, the ratio between products and reactants is still the same. So there's still 12 open circles for every 8 shaded circles, and this seems like the equilibrium constant if you kind of just divided it. And yeah, because the equilibrium constant for this reaction is B over A, and B are the open circles, so B over A, and that would be your equilibrium constant. So it seems like A is our answer, and let's move on. So let's move on to number 8. At 400 Kelvin, this reaction has a Kp of 8.2 times 10 to the negative 4. So this is the reaction. What is the Kp at 400 Kelvin for the following reaction? So note that our temperatures are constant, so we don't have to worry about temperature in this case. Now, what about the reaction now? It seems like something happened to this reaction, And because something happened to the reaction, our K will change, of course. So let's figure out what exactly happened. So the original reaction was this. Let me just write it out. And it seems like the Kp for this reaction is 8.2 times 10 to the negative 4. Now they doubled the reaction, so all they did was multiply by 2, and you get this. And it seems like the new Kp is going to be equal to this squared. So 8.2 times 10 to the negative 4 squared, because if you multiply all the coefficients by a factor, you are going to take your k to that power. This is one of the rules. So in your calculator, you're going to type 8.2 times 10 to the negative 4, and you're going to square it. And I get 6.7 times 10 to the, let's see, 3, 4, 5, 6, 7, negative 7. And just like that, our answer is A. So let's do number 9. The plot of the natural logarithm of the molar solubility, or S, of silver sulfate as a function of the reciprocal of the absolute temperature K is shown below. So what they did was they graphed this as the y and this as the x. And their graph looks something like this. Y equals mx plus b. Just like this equation over here, where y would be ln of s, and our m would, I guess, be negative 689.92, and our x would, of course, be 1 over t. And they would have a constant c there. But we need to figure out what delta H naught is. Now, how do we find that? Well, there is a way. If you remember from video 10.7, we talked about the Van 't Hoff equation that stated that the natural log of K, and this time let's make it Ksp since we are dissolving stuff and molar solubility is closely associated with Ksp. So, the natural log of Ksp is equal to the negative of the delta H naught of the reaction, and I'm writing naught because they specifically want us to find it naught, and this is over RT, and we have to add delta S naught of the reaction over R. Now this is the equation, and normally what you would do to find delta H is find the slope of the graph, which would be negative delta H over R, and all you would do from there is set it equal to the slope, which is negative 689.92, and you would get delta H. But that's not what we're supposed to do here. We don't have ln of Ksp, we have ln of this molar solubility. That's completely different, and therefore we have to modify our approach a little bit. So what I would do is find the way to make this Ksp turn into an S. Now we can relate Ksp and molar solubility through, the equilibrium expressions. So let's figure out how that works. So let's write out the reaction for the dissolution of silver sulfate. So this will become 2Ag plus, and these are aqueous, plus SO42 minus aqueous. And if we do an ice table, you can kind of see where it will go. So we have lots initially, minus x plus 2x and plus x, and in the end, we have 2x and x here. And we know that the Ksp for this reaction can be written as Ag plus squared times the concentration of sulfate ions. And we simply chug these equilibrium expressions in there, And what we do is we put 2x here, and we put x here. And you'll find out that this simplifies to 4x cubed. And if you remember, molar solubility is x because that's the amount of molar of this that's going to dissolve. So that would be the molar solubility. And therefore, we can substitute x for s, and we get that the Ksp is equal to 4s cubed. So we have a relationship between Ksp and s. Now, there's something cool that we could do. We could do something called substitution. So if we substitute this here, don't you think we would have ln of 4s cubed now? And aren't we a step closer to making a graph that looks like ln s is equal to, slope over t, well, the t is over here, plus c? Well, yeah, we're getting closer, but we're not that close yet. So let me do some erasing. So I'm going to erase this bottom part because we don't need it anymore. And we're going to play a little bit of substitution. So doing the substitution, we can say that the natural log of 4s cubed is equal to the negative delta H naught. And I'm not going to write reaction because that's kind of redundant. And we know that R is 8.31 times 10 to the negative 3 because we want kilojoules. And if we want kilojoules for delta H, we use this number for R. Now we divide this by T, of course, and we add delta S naught over R. Now we have to find a way to make it so that the equation looks like this. So up here, the equation looks like ln of just s is equal to some numbers in front of x, which is 1 over t, and we have to add a constant c. So we have to write it in that form somehow. We already have our 1 over t, but we lack our ln of s. So how do we make it so that this becomes ln of s? Well, if you know your logarithm rules, you can actually do this. So we can separate this into, let's see, ln of 4 plus ln of s cubed. And you know that ln of 4 plus ln of s cubed can be further simplified to ln of 4 plus 3 ln s. And this is all equal to negative delta H naught over 8.31 times 10 to the negative 3 times 1 over t. And we add delta S naught over R. Now what's the next step? So let me do some erasing because I ran out of space. And let me start at the top. So the next step we do is we want to be able to make it so that the ln of s is on one side, just like that, so we can make the equation y equals mx plus b. So how do we do that? Well, we can move things around, of course. So what we could do is we could subtract ln of 4 from both sides. So 3 ln of s is equal to negative delta H naught over 8.31 times 10 to the negative 3 times 1 over t plus delta S naught over R minus the natural log of 4. Now, how do we get rid of that 3? Well, that's easy. We divide everything by 3. So I'm going to erase this, and I'm going to divide both sides by 3. So if I divide both sides by 3, that 3 disappears, and we just simply divide every term by 3. So all this would be divided by 3. Now, this looks really complicated. I think we could kind of distribute this 3 to each of the terms. So that's what I'm going to do. So the natural log of s is equal to the negative delta H naught over 3 times 8.31 times 10 to the negative 3 times 1 over t plus delta S naught over 3r because we are distributing it to each term. So this is term 1, term 2, and term 3, and minus ln of 4 over 3. Now do we see something that looks like y equals mx plus b? Well, sure we do. This is y, so let me use a different color. This is our y. This is our x. all of this is our slope, and this is all our constant c. So we're doing great so far. We have the form y equals mx plus b, and we know the slope of the graph. And if we know the slope of the graph, we can calculate the delta h. And it looks like the slope of the graph of ln of s versus 1 over t is this guy over here. So we know that the slope is negative 689.92, and that's equal to the slope of this equation, which is negative delta h naught over, let's see, 3 times 8.31 times 10 to the negative 3. Now, in a different color, I'm going to solve this. So what I would do to solve this would be, well, I would first try to multiply this by both sides so that this cancels out. So, negative 689.92 times 3 times 8.31 times 10 to the negative 3. And I get that negative 17.2 is equal to the negative of the delta h naught. Well, guess what? If we divide both sides by negative 1, the negatives cancel out, and we're left with 17.2, and this is in kilojoules per mole of reaction, by the way, is equal to delta H. So it seems like D is our answer for this one. It was kind of complicated, but we did it. So good job, guys. So let me move on, and let's do the next question. So number 10 is a tricky problem. So let's go through this and think about what the answer choice is. A sample of SO2Cl2 is introduced into a movable piston with the pressure maintained at 1 atmosphere. So let's imagine a container with a cool piston, and this piston says, I want to be at 1 atmosphere no matter what. So this means that I can move up and down to maintain this 1 atmosphere pressure. So that's cool. Let's move on and read more. And the temperature is 450 Kelvin. The volume increases as the sulfurochloride equilibrates, wow, cool word there, according to the following endothermic reaction. So right away, since it's endothermic, we could write heat on the left side. Heat plus this thing is in equilibrium with SO2 and Cl2. Which change would decrease the number of moles of SO2Cl2 present in the piston at equilibrium. In each case, the pressure is maintained at 1 atmosphere. So just like what I said, the piston says, I want to be at 1 atmosphere no matter what. So this will be crucial in solving the problem because this piece of information will actually change everything. So our first condition is the temperature of the system is increased to 500 Kelvin. So if we increase the temperature of an endothermic reaction, it's going to want to shift to the right. And if it wants to shift to the right, that means that our moles of SO2Cl2 will go down and these two will go up. And because of that, this condition number 1, would decrease the number of moles of the SO2Cl2. So I like this answer. Now number 2 is complicated. A sample of argon gas is injected into the piston. Now at first, you're like, well, if I add argon gas, it's not going to increase the pressure of any of these 3 reactants or products. Therefore, it is not going to change the equilibrium, and therefore, nothing's going to happen. Because if we write the equilibrium, we could say Kp is equal to the pressure of SO2 times the pressure of Cl2 all over the pressure of SO2Cl2. And the thing is, this is at equilibrium right now. And if you add argon gas, it's not going to increase any of these 3 because you're not adding moles of this, or this. You're adding moles of argon, which would increase the partial pressure of argon. But since this is not part of our K expression, we don't care about it, and it won't affect the equilibrium going on here. So if you were me, you would have said that A was your answer. But guess what? That's not the answer. You want to know why? It's because of this very cool condition over here, where scientists said, we want to maintain the container at 1 atmosphere. Now this is a problem. So let's just say originally, of course, we're at 1 atmosphere, right? And we have some SO2, Cl2, and I don't really want to write all that stuff down. So I'm going to represent our reactants with closed circles. So this is our SO2, Cl2. And our products, I'm going to do it with open circles. So as you can see, this will all be 1 atmosphere. And remember, let's take a look at this equation that is so famous that you should memorize it. PV equals nRT. Guess what are the constants? T is a constant, R is a constant, and P is a constant. Okay, because they want to maintain 1 atmosphere, so therefore P will essentially be 1. So these 3 are constants, and essentially the 2 things that we could change are V and N. So what's the thing that happened here? Well, what the scientist did was that he or she pushed a sample of argon into the piston. So there's a problem here. If you add argon into the mix, they only put argon as the evil gas. So if we have an evil gas added here, so let's just say this is argon, then guess what? By adding that 1 particle of argon gas, well, we don't know how much there is, but I'm just going to assume 1 particle, we are technically increasing the number of moles of gas in the system. And guess what this equation says? For a constant pressure, which we want, a constant R, well, R is always a constant, and a constant T, the system will want to increase the volume because PV equals nRT states this. And therefore, by increasing the number of moles of gas by adding the argon, the system will want to increase in volume to maintain this 1 atmosphere pressure. Because if you think about it, by adding the gas, you're technically making the pressure of the container larger. So you want to increase the volume to alleviate this pressure. So what the piston does, it does this. So it wants to move just a little bit up to accommodate the extra circle. So I'll draw the rest of them in the color that I'm supposed to. So there are 4 of these. And this essentially increases the volume. So by adding the argon gas, you technically just increase the volume of the container because the container wanted to maintain this 1 atmosphere pressure, and it had to do that because you, the scientist, introduced argon. So guess what? Number 2 states basically we increase the volume of the container. So if we increase the volume of the container, that's essentially the same thing. Well, it's not essentially the same thing, but you can think of it as decreasing the pressure or alleviating the pressure. And in this case, we are decreasing the pressure of all 3 of these gases. Because if you think about it, originally, this gas had this much area. But guess what? This gas has a lot more area. And that means that the pressure is going to decrease since the molecules are not as clumped up together. So by increasing the volume, the partial pressures for each of these gases essentially just went down. So to make this more clear, we can take PV equals nRT. And we know that the moles of, let's just say, our reactants stay constant. So this is a constant, that's a constant, and that's a constant. And therefore, the only 2 variables that determine the partial pressure of, the gas is P and V. So P is, of course, the partial pressure. And by increasing the volume of the container, we can see that the partial pressure of an individual gas, such as, SO2, will go down. So by increasing the volume of the container, you did alleviate the pressure of adding that argon, and you did set everything back to 1 atmosphere. But by setting it back to 1 atmosphere, you decreased the pressures of all the other gases. So for this reason, we are essentially just decreasing the pressures of all the gases. And if we decrease the pressure of all the gases, which way will the reaction move? Well, if you remember, the side with more moles of gas will be favored, if there's an increase in volume, because if there's more space, more moles will want to form. So if there's more space, that means that there will be more SO2 and Cl2 that will form, and the equilibrium will shift to the right once again. And guess what? If the equilibrium shifts to the right, there will be less reactant, so the amount of moles of this substance will go down. And guess what? That means that 2 is also a correct answer, because it also decreases the amount of moles of this thing. So, because 1 and 2 are correct, this question is C. So that was a hard question, and hopefully you understood that explanation. Number 11. A gas X reacts reversibly and independently to form two different gases, Y and Z. So here we have two reactions, each with their individual Ks. At a certain temperature, the time evolution of the pressures of the three gases are shown. What is the equilibrium constant Ky at this temperature? So the first question I would ask is, what is Ky? Well, Ky, according to this reaction over here, is equal to the partial pressure of Y over the partial pressure of X. So the next question is, how do we find these equilibrium partial pressures? Well, we can do that by looking at a graph and seeing that the partial pressures flatline. And the moment that these partial pressures flatline is the moment when the concentrations are not changing. And when they're not changing, this means that the reaction has essentially stopped and that the forward and backward reaction rates are equal and they kind of just cancel out. So we want to see this, and these would be the equilibrium pressures, and we would just plug it in here to get an answer. But we have a problem here. We have a system that has nearly reached equilibrium, but not quite. And the reason I say not quite is because you can see this is still decreasing and this is still increasing. For that reason, this is not at equilibrium completely, but we could do an approximation, which is better than nothing. So I don't like D, because D is saying that it's impossible, we can't find it, it's too hard. Well, guess what? This reaction's so close to being done that we could at least try to find the equilibrium constant or make a good guess on what it is based on the trends we are given. So we're left with A, B, and C. Now what I would do is try to find the equilibrium partial pressure. So how do we do that exactly? Well, we have to think about this for a second and see where these three lines meet, or where they, end. So, of course, this line down here, which is the partial pressure of X, this is the partial pressure of Y, and this is the partial pressure of Z. We can see that X essentially just flatlines, and it's around 0.3, I think. Yeah, it's around 0.3. So we can say that the partial pressure of X at equilibrium is equal to 0.3 atmospheres. Now what about Py? Now let me tell you, the partial pressure of Py will not be at 2.8 because it hasn't ended yet. You can see that the curve is still moving a little bit. So let's do something called extrapolation, and let's extrapolate this line until, it reaches a nice even ending. So let me try my best to draw a straight line. So, it might go around here, it might, stop. And for this curve, PZ, it might, go up a little bit more, and then eventually might just stop. So, as you can see, the two pressures get pretty close to each other according to my extrapolation powers, and we can kind of estimate what the equilibrium pressure for Y will be. So, this actually lines up kind of over here, and that's around, I'd say, 2.4. So, the partial pressure of Y at equilibrium can be estimated to be around, 2.4 atmospheres. I wrote 2.7, sorry, that's 2.4. So now we can find Ky. Ky is equal to, 2.4 over 0.3. Now 2.4 divided by 0.3 is exactly 8.0. So if you were extrapolating this graph, you might make a mistake and you might say 2.5, but guess what? It's still pretty close to 8, so B is our answer. Now that's all for this video. I hope you learned a lot, and have a nice day, everybody.